Yeah. So we have seen the closure law. Each of those parts they are closed in that vector V, and then defined for a particular Euclidean space, which is the space 6. So the next law we just tested there is the commutative law. You can also go and test the distributive law, I mean the associative law, and then we'll also test what? The identity law. And so we call all these things axioms. Okay, so let's go back and see. So this one is commutative law. We have tested. Now let's go. The C is talking about U plus Z. So this one too is a straightforward thing. I don't think anybody will have problem with that. The D is 3U. This one too, I think is a straightforward thing. If you have problem, let me know. It's very straightforward. And the E is minus 7V. We know that minus, you multiply, you get that, right? F is also straightforward. At least if I give this type of question in the exam, all of you will be laughing. True or false? Now look at what happened with the G. U plus V gives you, or this type of matrix is referred to as the null matrix. I mean the null, the
It's
zero
B
what?
plus W.
Are we together?
Oh, yes.
And then look at the H also is the same. Okay. So notice that 0 times this element, it gives you this element, regardless of the values for the x1, x2, x3, x4. So whenever you multiply 0, I mean, this is not even called 0, this is called a null um, identity. With a given element, you get a null, and then you get a null matrix, or you get a null element. Now look at this one now. What is Z? Z is 0, 0, 0, 0. Okay, 2 times Z. So you see that when you multiply 2 times the null, you're going to get the null. Okay, so this is a law. Is that clear? Is
Yes,
that
sir.
clear? I want to go take you to somewhere now. Look, the zero vector, which we have just seen, this is called zero vector. Again, come up here. This is called zero vector. What is the zero vector here? Who can point? This is zero vector, right? You've seen it?
Yes.
Correct. That's the very
Yes,
zero
sir.
vector. Now, in Euclid, in this course, we always define the zero vector in n Euclidean space to be theta. It's always defined as theta. So anytime you hear the word theta, the first thing that comes to your mind is the zero vector. Is that clear?
Yes.
Now, this is another definition which
So
we're
come
going to see.
again. So come again.
I said we always define null
So
vector
come.
as theta. Anything we say theta is a null vector as far as this course is concerned. Is that clear?
Okay. All right,
So
sir.
if I say, form me a e to the power 2 null vector, what will be that vector? It will be x is equal to what? If I say
Theta.
e to the power 4, form a null vector in the space e to the power 4, that will be what? Theta will be equal to what?
0.
No. Theta will be equal to 0, comma, it will have 4 zeros because the Euclidean space is 4. Be very careful with this n. You understand? If I say give me a Euclidean space, I mean give me a zero vector with in Euclidean space e to the power 6, a null vector, huh? In the Euclidean space e to the power 6, what will be the vector? You have theta to be equal to what? Bracket open. You have the first zero, second zero, third zero, fourth zero, fifth zero. You stop at the sixth zero, right? Get this simple point clear so as I'm moving. If you have any doubt, you call me back. Is that okay? Yes or no?
Okay, sir.
Eh. Now, this is another definition that you must know. Now, this is a given vector. I've given you this vector x, okay? And this is the definition of this vector. And this vector is in the Euclidean space to the n power. Moses, Hello, Mrs. Moses.
She said she can't, that she will send the link, that she can't find it in her email. She just called me now.
No, she should check the link. Now, how did she join before?
She said she can't find the link, and I told her she should check. She said
It's
she
from
can't see it.
it's in her email now.
That's why I told her. She said she can't find it in her email. And she has joined
Just,
before. I don't know how.
just to
Maybe
forward the link.
you can forward the link to her because it's the same link. If you check, it's the same link you people is joining.
Uh,
Okay, we
okay,
want to
sir.
go. Okay, now see, I'm giving you this vector. Are we together? Hmm?
Yes, sir.
Now,
Yes,
there's
sir.
I can ask you to find the negative of the vector that was given. It means I'm saying get in another language we use for the negative is give me the mirror image. It means the negative of the when you say something is plus, the mirror will be the negative. Okay, so the mirror image of this particular vector will be denoted by negative. So we say the mirror of vector x is negative x. And you can see that all the entries of the first x will now have negative. So you have the negative one, negative of the first element, negative of the second element, up to the negative of the third element, right? So the mirror image of this is this. Is that clear? Now let's
Yes,
say
sir.
I give you this one now. I give you say let x be equal to 1, 2, minus 3, 4. Find the mirror image of this. The only thing that you need to look at if I give you these problems, if I find the mirror image, is this you're going to look for this x. What is the sign of this x? If the x was x, then the mirror will be minus. If the sign is minus, the mirror will be plus. Is that clear? So the same thing is find x.
So I
It
don't get
means
you.
I say if it is x, the mirror will be minus. If it is minus, the mirror will be plus. Is that clear?
Okay.
So if I say 5 minus x, now it means and then I say calculate this operation. It means this is what I say should calculate. Take the vector given and add to its mirror. What are you going to get? Anything added to its mirror will give you zero, will give you what? The zero vector. So this is what we're going to do. By definition, I've given you x to be this, then we're going to get minus x to be that. Now what I'm saying is if x is 1, minus x will be minus 1, 2, it will be minus 2, 3, minus 3, it will be plus 3, 4, it will be minus 4. So it becomes like that. So now when you add them together, you're going to get this vector. Is that clear?
Yes, sir.
Correct. Now, so this example illustrates the fact that for any vector x in the Euclidean space, if you take it and add to its image or to its mirror image, you're going to get a zero vector. And this is the part of this is the D of the theorem, and this is the D of the theorem. This is the theorem here. And what is the theorem? It means that that mirror image that I'm talking about is referred to as what? Inverse. Inverse. Is that clear?
Yes, sir.
How many of you are here now? I only getting your voice. What about the other person?
I'm here, sir. I
Okay,
can
that's
hear you.
good.
You know if you talk me, Abiodun?
Okay, that's good. Oh yeah, if you're doing or whatever, people should follow me. So this, in summary, this is exactly what we have done. I've given you. Have you sent a link to the lady?
If I want to send the link to the lady, I'll have to leave the class. I can't afford to miss anything.
Okay, don't worry. I'm recording. The lady will get it recorded. I don't know. She had
Okay.
the link. I don't know where the link went off. Okay, so you can see to form a vector space, this all these laws must be satisfied. Now, the question I can ask you is that proof. If I give you proof the first part that it is commutative. Now, the question is, this is a theorem or this is an axiom or a theory. Now it says that let x be equal to 1, x1, x2, up to xn. Y be equal to y1, y2, up to yn. Z is equal to 1, 2, up to, okay, so x, y, z, they are all element, right? Now, given this,
Yes.
prove that x plus y is equal to y plus x. Now, either I say prove this or I say prove the commutative law, or I can ask you to say prove the associative law. So for you to prove the commutative law, this is how you go about it. Please follow it very well because this step now I want to take is a little bit tricky. Now to prove this law, you have to first take the left hand side. The left hand side is x plus y, right?
Yes.
Right? So if you see
Yes.
x plus y, it means that we're going to take x and be adding to y. So the first element will be x plus y, which is the first element. The second element will be x2 plus y2, which is this. The third element will be x3 plus y3, up to the last element will be xn plus
Plus
yn.
yn.
Correct, that is it. So you have taken care of the first part. Are you there? Are you there? So
Yes, sir.
this addition in each of the components are, now what I'm saying, the addition in each component are addition in the set of real numbers. So all of these are in the set of real numbers. I will explain that to you very soon, what is mean. Now let's prove the second part now. We have taken this part, xy gives you this. Are you with me?
Yes, sir.
Now, since addition is commutative for real numbers, then you will just take, if I say proof, this is what makes this proof complete. You see, addition is commutative for all real numbers. Addition is commutative for all real numbers. Therefore, if we have x plus y, that is, this is the first element, which is this, up to this last element is going to be, you interchange y1 plus y2, the first element, up to yn plus nn, the last element. So you have seen that this part is this part is equal to, you reverse, and then when you reverse, you now say hence x plus y is equal to y plus x. Is that clear?
Yes, sir.
Thank you. Okay. Another one is very straightforward. That one will not be okay. Now the next thing is proof d part, which is very simple. If I say prove the d part, what you do is you just go, since x was given as what? Where is x? X was given like this. So you're going to find for minus x. When you find for minus x, you add them together, you realize that everything will be zero, then you get your null vector. Is that clear?
Yes, sir.
Yes, sir.
Now, the g part. Now, the g, where is the g? Okay, well, let's try to prove. Okay, let's look at the g part. Whether and let's just look at it. I think this is the G part. I want to prove this G. I'm proving this G. I want to prove that this left hand side is equal to the right hand side. To prove that, we already know what is x plus y. We have seen x plus y before, right? The
Yes,
first
sir.
one, this is it. So the only thing you need to do now is you cover the bracket and put R. So that's why we just cover the bracket and put our R, right? So if we do that, then we can now open this arrow and let it go to across. So this arrow will come to the first element, this arrow will come to the second element, this arrow will come to the third, up to the last element. That's why the arrow is going in. Is that okay?
Okay, sir.
That's good. So if you now open, this arrow goes here, it will be arrow 1, arrow x1 plus arrow y1. That's what we're seeing. Arrow x1 plus arrow y1, comma, arrow x2 plus RY2 up to RXN plus RYN. All this part is correct, right?
Yes, sir.
Perfect. However, We'll now take the second part. See the G, we're looking for the G. We want to take this part now. We are finished with this part. We have landed with this is the result of that part. Okay. Now the next one now is we take Rx. We're going to take R and only X. We'll take R and Y. So when we add them together, you realize that we're still going to get something of this nature. And if you look very well, this and this
Are
are
the
the same. So therefore, the law holds. Is that okay? So we have proof. You, we have been able to prove A, D, and G of this law. A, D, and G. You can go home and prove this, any of them. Is that clear? You just
Yes,
follow
sir.
the same
yes,
method.
sir.
Now, this is what I always tell my students. Now, this is B, E, and F. I can ask you to prove B, E, and F. This is B, E, and F. If I ask you to prove B, E, and F, what you should do, all of you have the right, you have the liberty to follow the theory. The first thing is you have to define your Euclidean space. The Mr. Abiodun's selection will be different from I don't know the other guy's name, sef. My classmate, I don't know his
Segun.
name.
Hello.
Shegun, But what happened is
Hello.
that your final result must be equal. Now, what happened is that if I ask you to prove B, E, and F, this is what you do. You will define your Euclidean space. So what I did here was I define my Euclidean space to be 1, -1, and 2. Okay? I get my Y,
Okay.
I brought this value, I selected it from my head because I'm dealing with set of real numbers. So you have to tell yourself that let your set of real numbers be a subset of the Euclidean space, e to the power 3.
Okay, sir.
So yeah, so now all these are the numbers I selected from my head. Okay. Therefore, I have to first prove this one. Okay. How to prove this one? We have already seen it before, but let's just prove it. So the first aspect is this aspect from year to year because I'm the one who selected my value. I brought it from my head. Okay. So you first take care of this part before you now come and add it to this part, right? So when you take care of this part, you will arrive at this answer, and then you come and add it to this one, and then you realize that this is your answer. Similarly, you will now keep your x and then take care of this part. You see, keep the x, take care of this part. Then you have this answer. You come and add it. Then you realize that they are the same. So you say, okay, since this one they are the same. If I want to mark, I don't mark all this jargon. I only look for this and this. Then I say, okay, that law has been satisfied. So which law is that? Which law? This is P.
Um,
Associative law has been satisfied, right? Hmm?
Yes, sir.
yes, sir.
Now, the E. Remember, I say you'll be the one to choose. So you will still maintain your X. The X that you selected before, this is the X. Okay? If you like, you
Okay.
reduce it. If
Are
you
the
like, you'll be the one at your liberty, select any three numbers. But mind you, the key word there is you must know the definition of the space I ask you to work with. If I say prove the associative law, prove any of the law, I say with a set of natural numbers. My brother, if I give you proof any of the law with a set of natural numbers, you will say it does not form a space because natural numbers start from 1, 2, 3. So if I say proof, you just say 1, 1 times the image, which is 1, I mean 1 plus the image, which is 1 minus 1, 0. 0 is not a member of natural number. So the law fails. Anytime your result does not give you the space you are working in, it means that the law has failed. Is that okay?
Yes, sir.
So you must be careful because I'm teaching you here now, but maybe in your exam I can put rational numbers. I say we need a set of rational number, proof A, B, and C, giving value X to be this. Like in short, we immediately just see set of rational number, just say you cannot go because Any rational number, let's say take a number divided by zero, you cannot go. So you just take that if this plus this, this number, say 2 divided by 0 cannot go, then it does not form. So it's not a member of that space. So you say the law does not hold. So what matters is the space I'm giving you to carry out your operation. Like this one now, this space is the space of real numbers. That's why every law here is working. All the laws that are working in the set of real numbers. I mean, real numbers. But it will not work in the set of natural numbers. I can give you numbers and ask you to prove. Okay, it's not does not show that it will not work. I can now give you there are some expression that will work. Whether you like it or not, you will think it will not work. It will work. Okay, I will show you what I'm saying when I move forward. So now in the E part, what is E? This is the E. E, we're having two scalar. We're having R and S. So you be the one to choose your R and S. You must make sure that when you choose your R and S, that R and S, you multiply it together, multiply by X is equal to, you keep the R, multiply the S and the X, then come again and multiply by the R. That's what that law says, right? So you
Yes,
come
Yes,
sir.
sir.
here, I decided to choose my R to be 3, my S to be minus 5. Then I decided to choose my X, any number inside that Euclidean space 3. Okay? So and I take the 3 times 5, which is going to be minus 15, then I now multiply throughout, I'll get minus 60, 30, minus 90. Then I do the same, I keep the R, which is 3, I'll multiply minus 5 and X, that is, this is the 3, minus 5 go in, then come multiply the 3, you realize that both the two sides, they are the same, right? So that law works. The last one, use the same value in E, use this value and prove the last one. This is the last one. The last one is saying that R plus S times the vector is equal to, you multiply the R and the S, I mean Rx plus Sx. Is it the same? The answer is correct. So you can see if you add the two together, 3 and minus 5 will give you minus 2. And then X was what? This. So this will give you minus 8, 4, minus 2. This is what I did yesterday. And then when you take this down one, you realize that the answer will still be the same. So you see that all the laws work, right? For set of natural numbers. Is that okay?
Yes,
Yes,
sir.
sir.
Thank you. Okay. Now, if you have understood, this is the problem. Example one, from the following list, capital A to E, pick all possible pairs of vectors that are equal. Let me see the first person that will tell me the first vector that are equal. I told you if the vector is equal, then what happens? Each of the elements must be what? The same. So which of the element here, which of them is the same? Which pair? Quick, 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 quick. Let me hear you guys.
That would be B and D.
B and no, B and D cannot be the same. But B, correct. You are correct. B plus something. B and B and E. If you multiply, if you open these brackets, you're going to get this, right?
Yes,
If,
yes, yes.
if you open this bracket, you're going to get this. So it's E, B and E, they are equal. This one will give you 1, and 2 will be. I don't think there's another one that is equal again. Have you seen how the problem can be twisted? Hello?
Yes, sir.
Somebody just joined or somebody left. Mostly, can you
He's not
imagine
here.
this woman joined me 10 minutes before your class? Oh.
I don't understand.
Wait, let me see. Let me call her.
Maybe she can't find the link. That's what she said.
Okay, let's move. Now check the second one. Another problem, just based on what we have just done now. I say let x and y be a vector in the x in this Euclidean space. Now I ask you, we have to define this, that is x minus y as this. She's communicating with me. Okay, we have to define this as this. And if I give you two vectors, I say prove this law. Are you with me?
Yes, sir.
Yes, sir.
Mm. You have to define, you must make sure that this plus is always there. But this is now the inverse that has brought come in. I know why I'm saying this because in multiplication, she says she can't find the link. And you say you people cannot go through your phone again.
I can't. Oh.
Even me, I cannot go back again because if I go, I will miss. I mean, let me just see if I can whether I'll be able to whether miss the class. Okay, it's only two of you. Um, and just give me 2 minutes. Let me see if she can come in because what I want to teach now is a little bit funny. Mm, wait, let me add. This I can add. Can you see? Are you able to see me?
Yes.
Yes. Money.
Okay. What is that her email said? Open now. I don't want it's taking my time.
Money about.
Eh?
No, you sir.
Not me.
He's saying
Yes.
triangles.
Has it gone? I don't know if the thing has gone. I okay. Okay. I think she will get it now. Um, check your email. Okay, let's come back. I'll
Ah.
give I'll give you this material. Okay, where were we? Okay, we're somewhere here. Let me go small. Now I said we have given
Work
you
to
this
do.
vector. We have given you this vector. If I ask you to find this is equation, oh, this equation. You get this equation.
Okay.
uh They say let x and y be these vectors in this space. Now define x minus y as x plus minus y. Setting x to be this and y to be this, write out the vectors x minus y. Is it difficult?
No.
Perfect. That's good. Who is saying no? I like the way we're going. Who is that?
Me, sir. Me, sir.
Me, your name.
Shagun.
Schedule. Okay, thank you. So, let's move. Now, the next thing is I want to quickly look at this. What do you understand as this identity, this sign, this E? Okay. Now, in this question number 5, we have this vector. Whenever you see E1, it means that the first entry is 1, the remaining element is 0. They are called,
Okay.
identity vectors. Okay. Now, if you see E2, it means that the first one is 0, the second one. So this E only symbolizes where 1 is placed. The remaining are 0.
Okay, sir.
So, so if you see
So,
E3, it
so
means that it's 0, 0. Eh?
I say it means this law operates between 1 and 0.
Yeah, no, what I'm saying is that, yeah, this law is just 1 and 0, correct? So if, for example, this is Euclidean space 3, so that's why we're having 3 elements. If I say Euclidean space 5, it means it will be 1 0 0 0 0 4 zeros. Then e to the e2,
Okay.
it will be 0 1 0 0 3 zeros. So it will expand up to 5. So when you say Euclidean space 3, it means we're going to have
Okay.
three. Correct. So now we can say a sum. Now, if we say these vectors 1, 2, 3, a sum of them is being formed in this manner. A is given by this, B is given by this, where A, B, C are real numbers. Therefore, anytime you form it, if you take a real number multiplied by these vectors like this, then you're going to get what is referred to as linear combination. And that linear combination is with respect to this. So if that is the case, then the question is, write the vector this as a linear combination of this. It's very straightforward, right?
Yes, sir.
Yes.
So it therefore implies that this E1, E2 can easily be, they are the same as I, J, and K.
So the first one will
Hmm?
be 3i
The first one will correct if you're getting me. Yeah, somebody is getting me. This one will be 3I minus 2J plus K. Or it will be
1k
3E1 minus 2E2 plus what? So if I give you this as a
plus.
form the linear combination, it's very simple, right?
Yes, sir.
Perfect. So I've already explained that, so you already know that. Then I'm just explaining this. This one giving x to be this, y to be this, calculate this. This one is also straightforward. Um, Now everything here is straightforward. So um, all this we've already done it. I will give you people this document. There's too much grammar to be explained here. Now, what I want us to look at here is now all this one we have done it. Mm, correct. No, it's this one. Page 11. Let me show you what. Please, I want to first of all know something. Are you with me?
Yes, sir.
Now let's look at this one. All these are examples. So I'm reading the example to explain to you. If we have this polynomial, say polynomial 2, whenever you see the word polynomial, if you see polynomial n, it means that the degree of that polynomial is n. If you see p sub to 3, it means that the degree of that polynomial is 3. This p stands for polynomial, right? So if I say p2, it means that the highest degree of that polynomial is 2. So that is why you see this is the if the polynomial if I say p2, it means that the polynomial is must be given in this form. F of x is equal to the coefficient times the highest, which is 2, because this 2 here represent this 2 here. Okay, so it starts to reduce. So it will start from the highest 2, it goes to 1, it goes to 0. Hmm? So if I say write a polynomial P4, give me official standard of the polynomial P4. It's very easy. All of you will be able to do that, right? If I say P4, it will be f of x is equal to
A
A4 x to the power
S of
4 plus A3 x to the power 3 plus
plus A
A2. Perfect. Are you there?
S.
It has Moses joined us.
Yes.
Hello, Moses. I don't know whether the name is, or the husband's name is Moses. Hello, Ma, are you
It
there?
is online.
She's online. Now let's look at this. I want to see how we can add these two polynomials. If I say add these two polynomials, this is polynomial f of x. This is also another polynomial g of x. Add them to form. Now, if I say the does polynomials form vector space? If I ask that question, it therefore implies that if I say polynomials of e to the power 3 or p subscript 2, do they form vector space? What am I saying indirectly? I'm saying that take these two vectors, these two polynomials. Now, these are the polynomials, right? Test for closure, test for associative, test for commutative, test for all those laws. Do they form vector space? Test. Now, what do you mean? If you do the test, if you take the first polynomial and add to the second polynomial, and the result is another polynomial, fine. Are you with me?
Yes,
Yeah.
sir.
Now let's look at it. Let's take the first one. The first law is A plus B must be equal to closure, right? If you want, I will
Yes.
go
Yes.
there. I will take you people there again. Um, where is it? People should be following me. These are the axioms. When I talk about axioms, I don't know. Some people call it axioms or you call it properties. Okay.
Yes, sir.
Mhm. I want to go. All these laws, I've already seen them. The closure law. I think I started it with it since. Where is it? Okay, it is here on this slide anyway. This is it. A plus B must belong to B. That means it means that if you have a polynomial, you add to another polynomial, it must give you a polynomial. Is that clear? Eh?
Yes,
Yes,
sir.
sir.
That is where we talk about the closure property. If I ask you if a polynomial form a vector space, the first thing if you take a polynomial, you add to another polynomial, it must give you a polynomial. So it is in that space. Then if you take a polynomial, you add to another polynomial, it's the same as you take the other polynomial, add to the first polynomial, it gives you the same result. Then you are the commutative law. So if I say, does P2 form a vector space? Proof. Show that P sub P2 polynomial in Euclidean space 2 form a vector space. It therefore implies that take any polynomial of your choice. Hmm? Test all these laws. Is that clear? Test all these laws for me. Is that clear?
Yeah.
All these five law.
Yeah, you can test. But the good news is that let me come here. Let me show you. Oh. For you to
Mrs.
test that
Joseph,
law, right?
please move your
Take,
mic.
tell her to mute that law. The baby is disturbing.
Please move your Mrs. Joseph. Please move your mic.
Has she muted?
Yes.
Okay. Now, for you to test this law very quick, right? If I say test it, what you should do is test this first one. Where's A? Hey, test this first one. Test the second one. Then test the another one. Where is this one? Where is the B part? Yeah. Test any of these. If this one works, let's say 1 and 2 for the B. Just test 1 and 2 for the first one and two for the second one. Then any other one will work. Are you there?
Yes, sir.
But sometimes, if you want to be a very sharp student, I will tell you this trick. If you just take for this B part, you test only this one associative law, this one, there is no way this associative law will work, and then it will not form vector space. If associative law works, it means it will form a vector space. But if you want to be more concise, you test the distributive law. If you work, bam, you just conclude. Since 2 and 3 operates, you say, therefore, it forms a vector space. Since 1, 2, since this one, since 1 and 2 obey, and then you come here, 1 and 2 again, 2 and 3 here obey, then it forms a vector space. There's no way they will not form a vector space. Is that clear? If you test these laws, oh, it must form. Oh. Are you there with me?
Yes, sir.
Oh yeah, let's go back to that question. Are you enjoying the class?
Yes, sir.
Okay. If you don't understand anything, let me know. So now let's see. So I said proof show that they can form a vector space. So we have given you this F. We have given you. I think this is another one. It's not that place. Is it the same place? I think I gave you F and G. Where? Sorry, I took it. So, hey, yeah, I gave you F and G. Where is it?
Man, I
Oh,
can't see. No,
are you seeing the bot?
I can't see the screen.
Okay, yeah, yeah, this is it. I gave you this is where I was. Can you see now? Hello, can you see?
Yes.
If you can see, let me know before I move.
Example 4.
Yes, example four. I was in example four. Now I said that this is polynomial two, okay, and this is the polynomial given in this form, where a1, I mean a sub with 0, 1, 2, they're all member of real numbers. Have you seen that? Define it and define and define additional and scalar multiplication as.
Follows.
Now this is f of x. So if this is it, they belong to this real number. So I can define my f of x to be this, and then g of x to be this. In that case, then we type the first one, f plus g. It means that take f of x and then add to g of x. So how do you do that? You take the first entry plus the second plus this other entry, then you factor out 2. The same thing. Have we been seeing that? Hmm?
Yes, sir.
So you see that this one to this one form, this one and this one is a scalar. So if you say this one was 2, this is 3, it's been a 2 plus 3, it's going to be what? 5. So it's just the same like this is a polynomial. And then this one now, the result also is a polynomial. So it is closed, right?
Yes.
Perfect. I was thinking you're not following. Okay. Now, another thing again, scalar multiplication. I told you that if you do scalar multiplication, it will work. If you work, then you're good. Then you say you form a vector space. You see that. Now, the second one, the one that will take you will do is the scalar multiplication. So you choose any scalar R that belongs to the set of real numbers. Most often, always try to choose zero. I mean, minus or zero, so that sometimes if you use zero, you go to a point where it is a number divided by zero, it is infinity, it does not work, then you conclude that it does not form a vector space. So that's why we always use scalar multiplication, because in this case, you are at liberty of choosing your arrow can be any number. Are you there?
Yes, I'm with you, sir.
Ehen. So now, if you take your that this is the law. This should be this is the law I'm talking about. The which law is this? You know the law, right? Let me know go and look for it. Okay.
Yes.
This which law is this? Distributive
Distributive
law.
law.
Correct. So now let's go ahead. So you take your f of x, you now put this, okay? It therefore implies that each of them you multiply by r. Okay. So in this case now, is this a polynomial? You see that it's a polynomial because how do you know it's a polynomial? This is a scalar, this is a scalar. So you see that the polynomial start from x to the power 2, goes down to x to the power 1, goes down to x to the power 0. That is what you're looking at. You're not interested in what is this value. Okay. So since this one gives you another polynomial, therefore P2 is a vector space. So if I ask you to do P4, is it a vector space? You will know what to do, right? Just test these two for
Yes.
me. Whenever I ask you, just do the two. Do the closure, and then you do what? The scalar. You're good to go.
Scalar.
Okay, now there's another thing. Closure follows easily from the definition since the right hand side of A and B are all polynomials of degree equal to 2 or less than 2. Then this is the commutative one. So in terms of commutative, f plus g, f of I mean x, is it going to give you g plus x? The same thing, right? I think it's a straightforward thing. If you look at it very well, it's going to give you, right?
Yes.
Because when you say a plus b, it's just the same like b plus a. 1 plus 2 is equal to, it's just the same like 2 plus 1. 1 plus 2 is the same like 2 plus 1. So that is, this law is called commutative law. So f plus g is equal to g plus f.
G plus
Does the
F.
law work?
Yes.
Yes, that's commutative law. So it's also work. So now this is the polynomial. So from here, everything can go. And you understand everything from here now. No need for me to go into details. Okay. Now, this thing that we are seeing here is just to tell you how we arrive at some laws in this course. For example, if you take this is z by dx x squared. It means bring 2 in front, then subtract 1. Okay? If anything you see here, you bring it in front, then subtract 1. Anything you see here, you bring it in front, then subtract 1. Anything you see here, you bring it in front, then subtract 1. So then from there, you can get the general formula. Anything you see here, you bring it in front, then subtract 1. This is a clear way of what I want to teach you people to easily identify something and then know how to move. Is that clear? I want to hear yes before I move to the next step.
Yes, sir.
I don't understand
No, you
that
have to
one I just
understand it.
left.
No, I said it's just a law that your brain should be very quick in seeing what I'm about to do. If you look at this one now, it says that it's the law is saying that if you see it like this, it means put 2 here, subtract 1. The same thing with this. Put 3 here, subtract 1. Put 4 here, subtract 1. Then if it is n, put n here, subtract 1. Is that clear?
Okay.
That's what I'm saying. Now, be very, very careful with what I want to go on now. Now, this sign, they are called definition. They are not normal addition. This read it. It is important for you to know that these are operations. Okay, these are vector operations. They mean definition. If you look at this, it's saying that this sign here, this sign that you are you seeing, which is called vector sum, it is not actually plus that you know. It is a vector sum saying that if you have x and y, the outcome should be x times y. This operator, that is what this operator is saying. Is that clear? Moses, who is there? Is
Sir.
that clear?
Yes.
Is
No,
that
sir.
now look at this operator.
No, sir.
This is a multiplication operator. There you understand this one now. Now look at this operator. This operator, which is multiplication, is saying multiplication. No, in a multiplication, we say dot. He's saying that
Yes.
if you see it, it's saying that take x raised to the power r. This operator is saying that take this x raise it to the power r. Come back again here. Look at
Okay.
this. Look at this operator. This is a definition, though. This definition is saying that this operator, which you are seeing here, is saying that take 2 multiplied by 3. That is what this is saying. It is not a plus. Be very, very straightforward. It's a definition that I'm showing you. Whenever I give you problem, I give you the definition. Now, what I'm saying is that we have to use this thing by following a kind of defined definition. This is sum. This is multiplication. But we don't just call it sum and multiplication like the normal sum that you see in your class, where you say 2 plus 1. If I put this sign and put it inside a bracket, you must ask me, sir, what is the definition of that your sum? Is that clear? If I put it inside this circle,
Yes.
put it down inside the circle, you must ask me what is the definition? Like now, if you look at this, my definition now, this definition is saying that even though it is a sum, but it's saying that it's defining, it's saying that take 2 multiplied by 3. That's what you see. So it continues like that. So it therefore implies that 4 of it, 4 and 6, it means 24. That means take 4 multiplied by 6. The same thing, 10 by 10. If this is here, because this is the definition, oh, it means that take 10 multiplied by that. Is that clear? Now, this is another definition of a point multiplication. This one is saying that take 3 and square it. That is the definition. So you take 3, you put the 2 in front. Therefore, implies that if this is then this one will be saying that one. Take 3, put 2 as the power. Take 3, put 2 as the power. Take this 3, put 2 as the power. If I give another one, say 4 circle dot 5, it will mean take 5 to the power 4. Is that clear?
Yes.
Thank you. If that is clear, then we can do a lot of things with it. We have to test for addition under that law. So now, if I say let's test for closure of addition, because we're saying test for closure of addition, this is like addition. But look at what this definition is saying. It's saying that if you see this side, it's saying that take x multiplied by y. That is why I see x multiplied by y, right? That's the definition that has been given.
Yeah.
So now say let x belong to vector space. Let y belong to this vector space. Then our definition of x is saying that x, if you say x, this is an additive, this is a summation sign. Sum y is defined as xy. Since x and y are positive real numbers and the product of positive real number is a positive real number. Therefore, this number too will also belong to V. Eh?
Okay.
Therefore, this definition, whatever result you get, will belong to V. The closure has been satisfied.
Ah. Mm.
Now, that is what he's saying. Now, let's put it this way. Let me say our x belongs to V. Let's say x is equal to -2, y is equal to 2, right?
Yes.
Now, the definition is saying we say x is equal to 2, y is equal to 2. Now, our Euclidean space is e to the power 1, just one element. By this definition, show whether it is close. So, what you're going to do is the first one, x is equal to 2, y is equal to -2, right? Isn't that what I said? 2 and -2, right? I don't know if I should be
Yes.
writing. I know this thing that I use in writing is not here. That's why I'm not writing. I don't know how
So I
to.
can continue understanding it now.
You're following me?
Yes, sir.
Okay. Okay. You can see the console.
Yes.
Okay. So if it is that case, then you're saying that by this definition, since x is equal to 2, y is equal to 2, and I mean x is equal to 2, y is equal to -2, they are all real numbers. Therefore, their products also will give you real numbers. And that product is xy. It will give you real numbers. Therefore, you are close under the set of real numbers. That's what I mean. Is that clear?
Yes,
Sir.
sir.
And then, I'm with you. Read this statement now. This one is saying that let X belong to vector space V. Let Y belong to vector space V. Then our definition of that our sign, that summation sign, is saying that whenever
Of
you
why?
get X, you get Y, you multiply them, just XY. Okay. 1 minute. Any good thing for me? The receipt. Oh, I thought this. Yeah, yeah. Okay. Are we there?
Yes, sir.
Yeah. So now we say since we are talking about X belonging to the vector space, V belonging to the vector space, and then these ones, look at this one, we are saying they're all positive, positive. So since X and Y are positive real numbers can be 2 and 3. And their product, if you take 2 and 3, when you multiply 2 and 3, are you not going to get 6?
Yes.
So the two positive numbers were positive, positive. Then when you multiply, you get another positive. So you get a positive real number. So therefore, xy, which is 6, still belongs to
Belongs to
that vector space V.
vector
Therefore, they
space.
are close. This law is close. It's close for addition.
Okay.
Is
So
that
when you give
okay?
us the question, I'm going to write the statement on
Yes, this statement, this course, this particular one need a lot of writing. I need to read all those things.
explanation.
Yeah, you have to write them. Now, in terms of, no, don't worry. Even though you see like this, we're going to do some examples which you're going to write. Now, closure for scalar multiplication. Now, here again, we'll talk about scalar multiplication. I've told you that whenever I give you something to test whether it forms vector space, just test for scalar multiplication and closure. If those two work, that means everything will work. Mhm.
Okay, sir.
So let R belongs to the set of real numbers. We have real numbers. And let R belong to the set of real numbers. And X belongs to the set of the vector space V. Therefore, we define our R dot X to be X to the power R. This is
X
our
is the
definition.
power of
Okay?
arrow and X.
Correct. It therefore implies that since X is positive real numbers, any real number, any real power of it is also a real number. Is it true or false?
It's true, sir.
It's true. So therefore, this operator is close
Is
for this is close, right? Therefore, this dot this belonging to this set V is also close for addition.
okay, sir.
Commutative for addition. We have this. Then let's take look at the commutative. Commutative means xy, it must be equal to yx. So if you look at commutative, we're saying that for you to say something is commutative, the x plus this plus, let me call it plus, right? Or let's say the x and the operator y will always give you this is the operator xy. Xy is just the same like yx, right? So if we have x, which is I mean x operator y, it give you xy. Then it's just and then you know that xy is the same like yx. Therefore, is going to also be y operator x. So x operator y is equal to y operator x. This is what commutative. I mean, this is a commutative. So commutative law has been proven correct for
Certified.
yes. For what? For the addition. So this thing you are seeing is called addition operator. Addition operator, but this addition operator has its own definition. Okay. So any question?
No question.
Eh?
No question, sir.
So now even this one, associative. So what I'm doing now is I'm taking people to another set of operators. Okay, where we're talking about vector space, we'll talk about span. Don't worry, people will soon understand me. So you see that closure has worked. Now we're talking about associative, commutative has worked, associative too. We say let X be a member of that, Y be a member of that, Z be a member of that. This is our associative. We have already seen that X, Y exists. XY is this, right? From our definition,
Yes, sir.
XY is this. It goes with Z. Is that clear? Hmm?
Yes, sir.
Then, by our definition, if we take this by this operator, it means that this times X. So this one is also the same, right?
Yes, sir.
So this is the same. Now, this is X, Y, Z. You cannot bring X also outside. X can be outside. And if X is outside, you want to write it in this way, you can still write it in this way. Since X is
X
outside,
operator
you want to
Y.
bring the definition of X operator Y correct. And then by this way, you can expand it to be like this. So this one now, we put operator here, it becomes this. So all this is from definition. So is it clear? Associative law, is it clear?
Yes,
You can prove that this side
yes,
is
sir.
equal to this side. It's clear, right? That's why I like teaching.
Yes, sir.
I like teaching small classes. I don't like teaching populated classes. You guys will follow me very well because it's straightforward. But some people will see Moses. Is she there?
Yes, sir.
Is it clear? I thought you have gone.
Yes, sir.
I'm recording the class anyway.
All right, sir.
Okay.
Thank you, sir.
If you don't understand anything, let me know.
I understand, sir.
Wow. And then I'll not ask you your. Let me ask you your question. How was your exam? Your full semester exam with me?
Sir, bless God, sir. It was okay, sir.
Manageable. Manageable. Okay, I
It
don't know
was
about that.
okay, sir.
Okay, now, now this is the next
Yes,
thing. Now,
sir.
additive identity. To determine, we have to determine what is this? This theta represent what? I'm asking
Zero.
you. Zero, correct? It represents zero vector. It's not actually zero vector. So to determine the theta, we have to ask for the equation. This and this operator is equal to x. That is the equation. Okay? And that is the operator. So now the next thing is to determine this, we have to ask for the equation this equal to this so that it should be what? Satisfied. So we have to take the left hand side. So the left hand side of this equation is equal to what? Let me see if you know. By definition, it will be x theta, right? By
Yes,
definition,
sir.
it will be x theta, correct. By definition, it will be x theta. By definition of this, it will be x theta. Hmm?
Yes, sir.
Yes, sir.
Therefore, if this is x theta, therefore theta must be equal to 1 for it to give you x.
Okay.
So we're going to see that this by this definition, our null vector will no longer be null vector. It will be something else, which you are going to see. You will realize now that your theta is 1. So all the time, theta cannot be 0. For this definition, under this definition of this sign, our theta now is 1 based on this. Because if it is additive, if it is say 1 plus 0, it will give you, let's say x plus 0 will give you x, right? But for this definition now, it's no longer 0. Because for you to make it, you have to say, okay, this it must be equal to x. Then by definition, this is saying by our definition of this is saying that this is equal to x theta. Now, for if you have x theta, what will make x theta to be equal to x? By when we take theta to be equal to 1, then we'll get x theta to be equal to x. Therefore, the that is the positive real number is 1. So it is the additive identity. So it's no longer 0. So the real number is this and only additive identity or 0 for this space. So in this case, it is 1. It's no longer 0, right?
Yes, sir.
So now what we're saying is that for that definition, additive identity now will be x1 to give you x. So where our 1
Yes.
is theta.
Okay.
Now, I think we're making sense now. I think I can move very fast. So the inverse law now by our definition, okay, this times the inverse, does it give you that theta? That is what we're saying. You know that is what I said. Something times its image will give you what? 0. But this one now, we have seen our
Zero.
theta
Yes.
is we'll see our theta is no longer 0, is 1. So this times its image is going to give us 1. That is what. So by definition, this will give you this dot that. That is to give you minus x squared, right? And with you,
Yes.
by definition. So therefore, the unique
Yes.
solution for minus x is if you want, what are you going to put for this minus x to give you 1? What you're going to substitute for this minus x to give you 1 will be 1 all over x.
Okay, sir.
So if you put 1 all over x, what are you going to put there to get 1? 1 all over x. So 1 all over x times x will give you 1. Therefore, this our minus here need to be substituted with 1 all over x. And since x is always positive, we know that 1 all over this must also be positive. So this also belongs to the set of V. Therefore, the inverse for this thing is 1 all over x. So the inverse for x is 1 all over x. It's no longer minus, it's not minus x. You can see that the definition matters a lot. Is that clear?
Yes, sir.
If you have any question, let me know. This is associative law for scalar multiplication. Here we have R. We have S, we have X. This is another definition. This is not another, this is the same definition I've given. So this is another definition now, not that one. Correct. Look at this definition. The other that time, that definition was summation definition, which says that X summation Y is equal to XY. Now this is multiplication operator, which you're going to put the operator inside the circle. The other one too, you're going to put plus. We'll put plus inside the circle, right? See. Hmm?
Mm.
Mhm.
Yes, sir.
So look at this operator. We want to look for associative law. It says that when you have this any value and this value, the result must be what? Anything you see here must be powered, must be the power. Is that clear?
Okay.
So
Okay.
if that is clear,
So it's power ROS. X power ROS.
mhm. So if that is clear, then we can now. So in this case now, we'll keep arrow, we'll work on this one. So when we keep arrow, we'll use this definition. If we keep arrow, we'll work on this one. You're going to see that this will just be x to the power s. Have you seen? We keep arrow. Yes or no? We keep arrow by this definition. This will be what? X to the power s. Hmm? Hmm?
Okay, sir.
And then finally, if that is the case, now this one now working with this, it will be like you keep this one to the power this. Have you seen that?
Yes, sir.
Any confusion?
That number five, you don't understand it.
This one where I underline.
Yes, sir.
This
Yeah,
that is
no,
very
that
straightforward.
one that you are doing recently.
This
Okay.
one, this one,
Yes.
this
Yes,
one,
sir.
yeah, it's straightforward.
Yes.
This definition, by this definition,
Okay.
we're trying to prove associative law for scalar multiplication. The scalar multiplication and distributive law says that what when we have this by this scalar multiplication, it means that whatever you have
The
here,
result is
square it, take it to the power. That is what you get
yes.
here. That
Okay.
is the law. Therefore,
Okay, sir.
if you have this
Yes,
spread
sir.
like this, you copy this, you define the law with these two, only these two. So you copy this, you define the law with these two. So if you copy this, by the definition, it means x to the power s. Now you have now one and two. So by the law again, by this law, you copy this, you raise to the power. That is what happened. Is that okay?
Hey, way.
Yeah, that is it. So by law of by the exponential law, when we have x to the power s to the power r is the same as you can interchange whether it's sr or rs. Therefore, what have we seen? We have seen that this is equal to this. So we have seen that the left
Mm.
hand side is equal to the right hand side. So we have proven what associative law
That.
under that definition.
Uh,
So I can give you an example and say let's define the scalar this operator like this. Let's define the additive operator like that. Prove that it forms associative law, closure law, identity law, inverse law, and so on and so forth. So you really want to be telling me all these things I'm telling you. First one, like I can say prove commutative law for it, associative law for it, identity law, inverse law, and associative law.
okay, sir.
And then the distributive
Now,
law
can we get
also.
the slide?
The slide there, I'll give you people. I'll give you plus the recording this thing, so you people can take it and look at it.
Okay.
Okay.
Have we been talking for more than 1 hour?
It's almost
Almost
1 hour. 1 hour 30 minutes.
I think
is
is it up
one
to that? We started what time?
It
seven
started
7:40.
7:30.
So it's only 8:50 now.
7:30. It's almost 1 hour 30 minutes.
Okay, so the distributive law is the next one to learn. So what is the distributive law? This is the distributive law that I want us to look at. Distributive law says that if you take this one multiply by 8, is it okay going to give you this? Now that is how you prove it by the definition. What is our definition? Our definition is whatever you have here, you take it to this power. So whatever you have here, this side will be the power. So you this thing, this side is the power. Now when you take this by the property of exponents, if you have x to the power r plus x, it's just like saying x to the power, I mean, it's just the same like this, right? This and this are the same, right? From exponents law, right? And with you. Answer yes or no, right?
Yes, sir. Yes, sir.
Correct. So if that is the case, now we put our additive law there. Why are we putting additive law? Because this is multiplication. So you are the one to put your additive law. You know that our additive definition means that anytime you have xy, it means it is x additive y. So now, since this is the multiplication, this one is multiplication, this one is, I mean, this one and this one in between is multiplication, right? So that's why we brought this identity, additive, addition, definition of addition. Okay, whenever we have multiplication, we bring addition, multiplication there, right? Now, the left hand side, if it is square, we cannot bring it to be this part. This side is saying that what? Copy this, put our law and the x. Copy this, put our law and the x. This thing, copy this, put our law and the x. So you can see that the left hand side is equal to the right hand side. Is that clear? Is that clear, Moses?
Yes, sir.
I'm happy. Oh, thank God. And now, in this one now, you can see this law here. We have taken care of this side. But when we take care of this side, we realize that the answer is this. Okay, the answer is this. Now let's see what happened if we have taken R, we have taken this section first, and this, right? Now this is the next one we want to take. So by by our definition, what is going to happen? We're going to copy the whole of this raised to the power this. Are we there?
Yes, sir.
Now, if we take the whole of this raised to the power this, it's just like, and then we know that anytime we see this plus, it means multiplication. This definition means xy. So, okay, we may decide to follow the same step like what I'm doing here. So, following definition, we copy this two, we leave this one. What is this definition? Xy, right? Additive, it means xy. So that's why we copy this. This is xy. The next thing is xy raised to the power r. That is what we have there. The next thing is we divide, we open it. Then the next thing is we put the sign, and the next thing is we go back just like we did. We realize that this side is equal to this side. This side is equal to this side. So our distributive law is okay. Is it true? Hmm? So I think when you go home, you can do everything that I'm showing here. I'll give people this material so that people will be able to take it and enjoy it. Hmm? Any question you can ask me. Okay. Hello.
Yes, sir. Yes, sir.
Yes, sir.
Okay. So now, if we look at what is referred to as, please, if it's my time, we're stopping at 9 o'clock or what? Let's stop at 9, right?
So my phone is low now. It wants to off.
Yeah, that's what I'm saying. The next 6 minutes, I want us to look at this word linearly dependent and linearly independent. Why, when we say something is linearly dependent, what do you mean? A set of vectors, say these are the vectors, is said to be linearly dependent if actually there exists a set of scalar. Let's say you have scalar, of which at least one is a non-zero. Such will give you a linearly dependent the vectors. So this is vector 1, vector 2, vector 3. Then these are the scalars. 1, 2, these are the scalars. Such that when you add this plus this is equal to 0. It therefore implies that this is linearly what? Dependent. Now to prove it, in this case, for us to prove that, then k must be equal to k1 must be equal to k2 must be equal to k must be equal to 0. If all these k's are not equal to 0, then this thing cannot be linearly independent. I mean linearly dependent. Is that clear? So if I give you a set of
No, sir.
vectors, if I give you a set of vectors, and I say prove that that set of vectors is linearly dependent, it means that you have to look for the value for the scalar that I will give you to make sure that it must be equal to 0. If any of the k's are not equal to 0, then it's not. If at least one is not equal to 0, then it is not linearly dependent. But if all the k's are equal to 0, then it's linearly dependent. Like for example, if you look at this one now, this is vector, this is the k, which is a scalar. This is vector, this is a k, which is a scalar. This is to the n, which is a scalar. So it must be equal to 0 to get this definition linearly dependent. So for example, now if for it to be linearly dependent, k1, k2 up to k to the kn must be equal to 0. If that is the case, then this is said to be linearly dependent. Then the other side, the reverse, if these are also the vectors and any of the k is not 0, therefore it is linearly independent. Hmm? Let's take for example now, show that these are the vectors, the set of these vectors, these, show that they are linearly independent. If I say show that this set of vectors are linearly independent, what am I going to say? If I ask you, what you do is you're going to put your k because they are just two, so you put two k's. The first k must be equal to 0. The total number of elements inside must be equal to, they must be the same. So what you're going to do now is you're going to solve for k. This for here now you have k, this will have k1 plus k2, and this will have a k1, 2k1, 3k1 plus 2k2 minus 2k2 and 0 must be equal to 0. Then you add them independently, okay? In this case, you have k1 plus 2k2 is equal to 0. Then you also have another number, 2k1 minus 2k2 is equal to 0. And then you have the third one, 3k. So you realize that by the time you solve, you see that k1 is equal to k2 is equal to 0. So if all the k's are equal to 0, then they are linearly what? Independent. They are linearly dependent. Are we together?
Yes, sir.
That means they are linearly independent if the k's are equal to 0. Okay? If all these k's are equal to 0, then the vectors they are linearly independent. But if we say they are linearly dependent, then the k must not be equal to 0. So if you see this one now, show that they are linearly independent. That means, see, in this case, when you solve it, you realize that your k is equal to 3, k is equal to minus 2. So they are linearly dependent to each other. I would think I'll stop the class here. Do you people
All
know
right,
how to
sir.
solve this? You know how to solve this, right?
So that number one. How
No,
do we
it's
get
just
zero?
no, it's the definition. The definition is saying that if I give two vectors, I say prove that they are either linearly dependent or linearly independent. You're the one to introduce your K. I decided to introduce K for your class. Last year I introduced C. I can decide to
I know, sir.
introduce and then look for C. I can decide to choose I can decide to use A, B, and C. But make sure that A equals to 0. But here I use K1 and K2 because we only have two sets of three elements. One, two, three, one, two, three. So if for example I have one, two, three sets, then we're going to have K1, K2, and K3. Is that clear? Like we check it here. We have how many sets here? N sets. This is vector 1, vector 2, up to n. So here we only have two sets, vector 1, vector 2. So we're going to have only K1 and K2. So we're going to solve. So when you solve this problem, you realize that K1 is equal to K2 and is equal to 0. When you solve it. Is that clear?
Yes, sir.
And the same thing with this one. And then this one, you're the one to make sure if I say test, you go to put K1 plus K2 is equal to 0. And then you solve for K1 and K2, just like you get a kind of a simultaneous equation. You solve it, and that is the end. That's good. So when we come back next class, we'll be talking about matrix. Matrix is very, very interesting, straightforward. I don't think we'll have so much to do. I will call Dr. Gundele to know which part of the course he's taking so that I don't go too much with you people. Okay? But if it is left for
Okay
me,
then.
we're going to finish 450 pages. The book I'm using, I'll send to you people. This one is just 89. We're now on page 89. Okay.
All right, sir.
So how was the class?
It was very interesting.
That lie was not interesting.